Problem number 12. A 50 grams piece of clay is thrown horizontally with a velocity of 20 meters per second, striking the bob of a stationary pendulum with length L equals 1 meter and a bob mass of 200 grams. Upon impact, the clay sticks to the pendulum weight and the pendulum starts to swing. What is the maximum change in angle of the pendulum? Solution for problem number 12. Use the equation for inelastic collision small mv equals small m plus big mu to get the velocity of the bob is 4 meters per second. Then use energy conservation h equals u square over 2g to get the height of 0.8 m. From there it is just trigonometry to get the angle theta equal arc cosine 1/5. This is answer A, and that was solution for problem 12. The following information applies to problems 13 and 14. Angela the puppy loves chasing tennis balls, so her owners built a tennis ball launcher. It fires balls along the floor at some initial speed, applying no rotation to them. The balls initially slip along the floor, then start rolling without slipping. Ignore the potential deformation of the ball and floor during this process, as well as air resistance. Problem 13. Which of the following plot pairs could show the linear speed v and rotational speed omega of one of the balls, over time? Assume the floor has a constant roughness. Solution for problem 13. As the ball is rolling while slipping, the friction force acts to reduce its linear momentum and to increase its angular momentum. The change in the angular momentum is proportional to the change in the linear momentum. The ratio depends only on the moment of inertia of the ball. The friction force will be constant until it drops to zero. This means that the plot of the linear speed should decrease linearly until it hits a constant level, and the plot of the rotational speed should increase linearly until it hits a constant level at the same time. This is answer A, and that was solution for problem 13. Problem 14. There are 3 kinds of balls that can be launched in this setup, all having the same radius r. First, a regular tennis ball, a thin spherical shell of rubber, of mass m1. Second, a solid wooden ball of mass m2. Third, a solid rubber ball of mass m3, where m1 less than m2 less than m3. All 3 types of ball emerge from the launcher with the same velocity. For which ball will the final velocity be highest? Solution for problem 14. The frictional force provides a linear deceleration of delta v over delta t equal negative mu g, where mu is the coefficient of friction. It provides an angular acceleration of delta omega over delta t equal mu g r m over I, where m is the mass of the ball and I is its moment of inertia. We're waiting until omega r equal v, which means that we care about delta omega r over delta t equal mu g m r square over I. The quantity, m r square over I, is larger for objects where the mass is close to the axis than for objects where it is far away, so it is larger for a solid ball than for a spherical shell. This means that the solid balls will pick up angular velocity faster and will end up with a larger speed at the time when the ball stops slipping. It means that balls 2 and 3 have the same final speed, which is greater than for ball 1. This is answer D, and that was solution for problem 14. Problem number 15. A uniform rigid rod of mass m and length 2L is attached to a massless rod of length L, which is fixed at one end to the ceiling and free to rotate in a vertical plane. The massive rod is connected to the free end of the massless rod. Suppose an impulse J is applied horizontally to the bottom of the massive rod. Determine the relationship between the magnitudes of the angular velocity omega small of the massless rod and omega capital of the massive rod immediately after the impulse is applied. The moment of inertia of a uniform rod of length d and mass m about its center of mass is given by I equal 1 over 12 md square. Solution for problem 15. We need to find the speed v of center of rotation and angular speed omega of rotation. This just after the impulse, the speed we can find from the formula mv equal j. So v equal j over m. Angular speed from the formula 1/3 ml square omega equal jl. So omega equal 3j over ml. Now we can find the linear speed of the upper end of the heavy rod, which is simultaneously lower end of the massless rod. That will be v1 equal v minus omega l, which is negative 2j over m. It means that angular speed of the heavy rod is counterclockwise and weightless is clockwise. And omega equal v1 over l, which is 2j over ml. Finally, big omega over small omega equal 3 over 2. That was answer E, and that was solution for problem 15.